Good afternoon, everyone. Thank you for attending today's webinar on ventilation versus infiltration versus manual J. This webinar will be recorded and the recording is available to all attendees on that Google Drive link that's sent out in the follow-up email. If there are any issues with audio, please write me in the chat. My name is Erica DeLello and I'm a project manager for Noresco. This series is sponsored by the Colorado Energy Office with training materials created by BuildTank. So we've been working with the Colorado Energy Office to provide trainings just like this one. Here we have a list of the webinars that we have offered in this series, and we'll likely be adding more to this list. So keep an eye out for an email from me over the next few weeks. And then if you do see another webinar on the list, feel free to click the link in that follow-up email if you want to register for another one. In addition to that, we're offering tailored group trainings or technical assistance to jurisdictions or industry professionals. So feel free to follow up with me on that as well. In addition to that, we've put together a code adoption toolkit that reviews the cost implications of changing code cycles, the benefits, and a lot of other compliance resources. Well, I've been working with the subject matter experts to keep adding to that code adoption toolkit and make sure it's up to date. So, and in addition to that, there's a troubleshooting guide that covers iCode conflicts, alignments, clarifications, and passive compliance. And both of these resources can be accessed through the Colorado Energy Office's website. Throughout the webinar, we do want to encourage questions. So there's a little Q&A function on the bottom of your screen. And that function can be used if you'd like to ask a question. There's also the chat, which can be used to chat among participants. But if you want to ask a question, I'd ask that you use the Q&A function. There is also the ability to raise your hand. So if you want to ask Robbie here a question directly, by all means, just raise your hand and I'll unmute you at the end of the presentation. And then there's a survey window at the end that will pop up following the webinar. Please take a minute to provide feedback on that. I've been using that feedback to improve these webinars and give that feedback over to the subject matter experts as well. So today's presenter is Robbie Schwartz, and Robbie founded BuildTank Incorporated to be a practical building think tank to do research, education, and work with builders to ensure their homes not only comply with the energy codes, and programs, but also perform. So at BuildTank, they strive to use what they've learned from their fieldwork to affect meaningful change in the construction industry. So with that, Robbie, I'll stop sharing my screen now and you can take control.
Okay. I think we are shared now. Everyone can see my screen. Thank you so much, Erica, and thanks everyone for taking part today. I'm going to stop my video while I present, and then I'll come back on the video at the end here. So today, like Erica said, we'll be talking about infiltration and ventilation and manual J. It's kind of the idea is that it's an add-on to what Gil had been doing with manual J, D, and S. And we're really kind of focusing on how do we understand manual J in relationship to the building thermal envelope, and what things on the manual J will we be looking at in particular to get a better idea of if the manual J was done correctly here. So again, we'll talk quickly about why we're having this conversation. We'll be talking in depth about the building thermal envelope and how air moves in a home. And then we'll get into infiltration, ventilation, and other things that impact the manual J. We'll talk about 8 specific things that impact the manual J that should be looked at and reviewed to ensure that that manual J is going to be as accurate as possible for any particular house that it's been developed for. So to begin the conversation, we really need to understand that our HVAC system will not work and really will not work at all unless the building thermal envelope is clearly defined and is executed in relationship to the manual J. So there is this synergistic relationship between the HVAC system and the design of that HVAC system and the overall performance of the building thermal envelope. What we know is that energy is gained through our building thermal envelope and is lost through our building thermal envelope. And we need to have a sound building thermal envelope for a right-sized HVAC system to actually perform in that building thermal envelope. So when we're looking at the performance of the building envelope, we need to not only look at is the specification or insulation or air barrier system, the different control layers in that home, are they there? But we need to look at how they've been installed and if they've been installed so they actually function and work in relationship to the greater performance of the house, but also in relationship to what was designed in that HVAC design process there. So if we look at a quick design process for a house and construction process for the house, we see this schematic that takes us from initial design through the completion of the project. And we have that same sort of diagram for the creation of an HVAC system where we have the design and load calculations happening. And what we see when we look at these in relationship to each other is that the HVAC design process happens very early on in the design process of the house. So we're making a lot of assumptions in this case, and we need to realize that the HVAC contractor who's doing a design for the HVAC system is assuming or using the specifications that the architect or builder has put out there for the insulation levels and whatnot, but they're making some assumptions about how airtight the house is, how well the building thermal envelope will be executed when it's actually constructed, what type of overhangs are actually going to be achieved to shade windows, potentially what type of blinds are going to be put on the inside of the house. So all these different things are looked at, but they're looked at very early on in the process. So we have two situations that ultimately get created. One is that the HVAC designer is going to assume that everything that is specified is going to be executed perfectly, and they'll do a completely right-sized calculation for the house. And what happens if that isn't the case? Or that HVAC contractor is going to make some assumptions that the specifications and construction isn't going to go absolutely perfectly, and they're going to make some adjustments to their design to ensure that they're not going to get a lot of callbacks for comfort and whatnot, which tends to oversize the equipment or potentially undersize the equipment. Now, this HVAC design process has three major steps, and they're not that difficult to do because we have lots of good software out there, and they're defined by ACA through manual JDNS. But the first step is to calculate the heating and cooling loads. That is what the manual J process is all about. The second step is to select the equipment with the capacity to meet those loads, and that's what manual S is about. And the third step is to actually design how those loads are going to be delivered around the house. That's the manual D part. How do you design the duct system to deliver those loads? Now, this process, especially step one, again, is using those assumptions about the thermal envelope and what R values are being created or used around that building envelope to separate conditioned space from unconditioned space. And the assumption is that those R values are going to be installed so that they're actually achieved in that building thermal envelope. Because ultimately, our goal in an HVAC system, in conjunction with that thermal envelope of the home, is to create a house that has even temperatures from room to room and floor to floor. But the reality is out there that that thermal envelope might not be working as well as we hoped it would be. So we end up oversizing the equipment to compensate for that. Or if instead of having the right building envelope where we can have a right size system that actually works and performs for the house. So let's get into a little bit of the building science and some of the things that are taken into account in these load calculations that are pretty big variables there. And the first ones we're going to be talking about is this infiltration versus ventilation. So let's quickly define these things. Now, air leakage is described as infiltration and exfiltration. And infiltration and exfiltration are basically the opposites of each other. But what we understand is that infiltration is this unintended and accidental movement of air. And same with exfiltration is this unintended and accidental movement of air. However, infiltration is the air coming into the home and exfiltration is the air coming out of the home. So air is moving in and out of our houses by different pressures that are impacting that home. And we don't have a lot of control and we don't have any predictability about when that's actually happening. The infiltration is accounted for in the HVAC design, and we can measure the infiltration and make it more precise in its accountability in the HVAC design if we use a blower door. So we'll learn a little bit later on if there's an assumption that you can make on how airtight the house is, or you can use a more accurate measurement that comes through the blower door there. But ultimately, what we're striving for is to get this control and predictability of air leakage. And that's one of the reasons why we want to build our houses as tight as we possibly can, because we will know in our calculations that we are taking into account the correct BTU load for that infiltration and exfiltration, that overall air leakage that's happening in our house. Now, this is a little bit different than what happens with mechanical ventilation. So mechanical ventilation is all about control and predictability. We know a specific rate or cubic feet per minute of air that's going through that house, in and out of that house. And we've set that air rate at a specific schedule and how often that air is transferring from inside to outside the house to properly ventilate that house. And that's really important to understand that it's different than random air leakage that's happening through infiltration and exfiltration in our house. And these loads are accounted for in the HVAC design separately than that infiltration load that's happening, that air leakage load that's happening on the house. Now, the other thing that is a little bit confusing to people is that ventilation can happen in a number of different ways. You can have exhaust and supply ventilation, or you can have balanced ventilation systems in your house. Exhaust and supply ventilation systems, although they use the same holes that air is moving through for air leakage and infiltration and exfiltration, it does continue to put that air that's moving in and out of the house at a specific rate and a set schedule. So we know exactly how much air is moving in and out of the house. We just might not know exactly where it's moving through or what holes it's moving through. So it's really important to count mechanical ventilation and infiltration as two separate and distinct loads that are incorporated and designed for in that manual J process. Now, there are some ventilation systems that are able to provide these additional functions, and those are generally balanced ventilation systems that can tell you where the air is going in and out of the house and the specific source and location where that's happening. And you might also be able to add filtration to that air and to be able to distribute that air in better means there around the house. But the primary function overall of mechanical ventilation, regardless of the type of ventilation that you're using, is to provide fresh air for the occupants and to provide background moisture control in our houses. And that ultimately helps us achieve better comfort, efficiency, and performance in our homes if we have good ventilation systems and we've built our houses as tight as possible to limit the air leakage load or the infiltration load that's happening in our houses. So again, the important part here is to have a clearly defined building thermal envelope and to execute that building thermal envelope really well, because the loads of these two houses are going to be completely different if you have a clearly defined building envelope versus one that is not executed well or defined well. And so the IECC is beginning to help us with this process. As of, I believe, the 2015 IECC, the building thermal envelope shall be represented on the construction documents. And this is just one example of how it could be represented on the construction documents. What we also know is that the IECC defines the building thermal envelope, and is defining the building thermal envelope as these different assemblies that come together to create this boundary condition that ultimately separates conditioned space from unconditioned space. So we have the alignment of our air barrier systems and our thermal barrier systems coming together, again, to give us this clean separation, this clean boundary that separates conditioned space from unconditioned space. And so what is that ultimate boundary? Well, the IECC also defines these things as well. It defines this air barrier system that is this grouping together of different materials and assemblies that are joined together to create this continuous boundary condition between conditioned space and unconditioned space. And the IECC says that we have to have a continuous air barrier, and it defines that continuity of that air barrier in our system. So this depiction of the thermal envelope is taking this building science principle of this red line test that building scientists like Joe Stiebrick and others have been talking about for years out there, and it's putting it into action so that we clearly define the building envelope, and then as the architect sends those drawings into the field and to the HVAC contractor and the builder and insulator and so forth, that we actually get that envelope executed and executed properly. But what we also need to understand is that that single line, that single red line, is not the true barrier between conditioned space and unconditioned space. Remember, we have to go back to our definitions that this is an assembly of things, and we're really relying on this belts and suspenders approach to get this boundary between conditioned space and unconditioned space. So we might have a condition like this, and this is why I like to define the interior and exterior components of that air barrier system there. So you'll see materials that are coming onto the market like Aero Barrier, for example, that is using a propellant to tighten up the house, and it's primarily using the interior drywall as the defining air barrier of the house. But the reality is that that drywall by itself can't do the job completely. So we're looking at, in its simplest forms, we're looking at the interior drywall as the primary air barrier on the interior side of the house. And the code goes through a table that tells you, well, where there isn't continuity in that drywall, like behind a tub on an exterior wall, for example, you might have to add a supplemental air barrier at that location. And then on the exterior side of the house, the exterior sheathing would be our primary air barrier system on the exterior of the house. And so the combination of these two things in these assemblies that surround our house, we have a belts and suspenders approach to get a clear thermal envelope of the house that can literally separate that conditioned space from the exterior in a tight, well-constructed assembly. So some might ask, what's the house wrap then? What is this house wrap supposed to do if it's not the primary air barrier of our home? Well, the reality is that the house wrap is usually a drainage plane. We know that moisture is going to bypass our exterior claddings. So we have this drainage plane where moisture can drain down and out and away from the structure. So the drainage plane or house wrap generally just is not installed well enough to be a true air barrier system. It can be a supplemental air barrier system. in this belts and suspenders kind of process that we're trying to build here, but it's generally not the primary air barrier on the exterior side of our buildings there. Now, the function of all these things, this building thermal envelope that we have created with the interior and exterior sides of the assembly, is to enclose insulation so that we get a 6-sided enclosure of that insulation in wall systems and floor systems, so that air permeable insulation will be able to trap that pocket of air and actually work and function. And so ultimately we have better air control, thermal control, and moisture control inside of our homes here. Now, the next thing that we see with regards to the thermal envelope and the IECC is that the IECC says we need to install our insulation and air barrier systems in accordance with manufactured instructions. And it gives us a little bit more detail in other sections of the code, but in general, we need to understand what the manufacturer is trying to achieve here. And so the reality is that insulation works the same way that insulation works in our bodies as it does in our houses. So this person is wearing a fleece jacket, and it really doesn't matter if she's wearing a fleece jacket or a wool sweater or a cotton sweatshirt. The objective of this material is to trap a pocket of air. And if we have a stagnant pocket of air, we can develop some R value or resistance to the flow of energy. So it's the stagnant air pocket, not the material, that creates that R value. And the problem with air permeable insulations like cellulose and fiberglass, for example, or in this case, fleece jacket or wool sweater, is that that pocket of air can move around if you introduce wind to it or air movement that's going to move through the material. So we need to get an air barrier on top of the thermal barrier. So with our clothes, we use a nylon shell as that exterior air barrier. We use the fleece jacket in this case as our thermal barrier. And then we have our skin as our interior air barrier system here. And we've been able to stop the movement of air or wind from scrubbing those air pockets away. And we've got a system that actually works now. In our house, it's very much the same. We have a fiberglass insulation or air permeable insulation in this case. It does resist conduction because it does a really good job of trapping air pockets in that insulation, but it doesn't, and it's not able to resist the flow of air through that material there, unless we enclose that cavity with a air barrier on all 6 sides to be able to limit and hopefully stop the movement of air through that. So we're really talking about cavity insulation, so our wall cavities and our floor cavities. When we talk about ventilated attics and whatnot, we're talking about a little bit different process here that we just don't have time to go into today. But remember that the myth of insulation, especially fibrous insulation, is that it stops the movement of air. And that comes, that understanding comes when we begin to realize that there's air permeable insulations on the market and there's air impermeable insulations on the market, or insulations that air will not move through. But both of the insulation types, their objective is to trap a pocket of air. And that pocket of air, again, is the primary thing that's resisting the flow of energy. So whether it's fiberglass bats or a closed cell foam, they're both designed to trap a pocket of air. The fiberglass bat or cellulose or blown fiberglass, we have to add those additional air barrier systems to, whereas depending on the depth of the blow of foam products, or if it comes in a board or not, will determine its ability to stop the movement of air as well. So the table R402.4.1.1 is the air barrier and insulation table. And that table is a table that defines the different components of the house down the left-hand side of the column there. It gives us additional criteria or specifications for how to install and where to install air barrier systems that goes beyond the manufacturer instructions. And in the same way, it gives us additional installation criteria for insulation in these different components. So as I said before, like that tub on the exterior wall, it's telling us in this table that we need to add that supplemental air barrier because the drywall system isn't going to have the continuity behind that tub there. So it's an important table to understand in order to create that tight house and create that thermal envelope that we can use in our manual J calculation. So we're going to change our conversation here a little bit and talk more about airflow in our houses on the infiltration, exfiltration side of the equation and ventilation side of the equation here. So the first thing I like to do when I think about air moving in our houses is to think of air as a freight train. Air is a freight train because a freight train carries cargo from point A to point B, and air is carrying cargo as well. And the cargo it carries is energy or heat, pollutants, and moisture. And it's really the moisture and the energy that are the critical things that it's moving around. But we're seeing more and more emphasis on air quality as well. So the pollutants are pretty important as well. When we think about air, this is a question that comes up quite often. Can a house be too tight? And I hope everybody understands that the resounding answer to that question is no. Our houses can't be too tight. Our houses don't breathe. What we want is that house to be as tight as it possibly can be so that we can control and have predictability of airflow, thermal flow, and moisture flow, because that air is carrying heat and moisture that can create condensation and other building durability issues in and around our houses there. So what's the real question we should be asking is, are our houses underventilated? And the resounding answer, unfortunately, still is yes, our houses are underventilated, even though the IACC and the IRC say that we have to not only build our houses tight, but we have to ventilate them correctly. So build tight and ventilate right is kind of the mantra that we need to build to and inspect to ensure that it's happening out there and ensure that ultimately our thermal envelopes and our HVAC designs are matching and working synergistically together to achieve comfort and performance in our homes here. So what type of control do we want of that air? And what type of predictability do we want of that air? Well, we want the predictability in the same way that McDonald's has created predictability. If I order a Big Mac sandwich here in Denver and I order one in New York or in Paris or in San Francisco, I know exactly what I'm going to get because they have done such a good job of controlling the process that they have great predictability of the result that they're going to get. So I know exactly what it's going to taste like in all of those locations. I know exactly how I'm going to feel after I eat it there. So regardless, we want to understand and have that same type of control and predictability in our houses. So we need to understand a little bit about how air moves in our houses. And the reality is that air moves only if there is both a hole and a pressure difference or driving force across that hole that will move air in or out of that hole. And we happen to have a lot of holes in our houses, and that the table I just showed you and other locations in the code are helping us get tighter and tighter homes and seal up those holes that we see most often. And it's also telling us to seal up all the holes in our building thermal envelope so that we can get that tight house. So if I look at a balloon here and I equate that balloon to a home, the rubber membrane of the balloon would be the thermal envelope of our house. And if I have equal pressure inside the thermal envelope and outside the thermal envelope or outside the rubber membrane, I'm not going to get any airflow across that rubber membrane or across that building envelope because I don't also have a hole. But in this case, I have a string that I can untie and create a hole. And if I untie that string, I've introduced a hole and I've changed the pressure dynamic here. I now have greater pressure outside the rubber membrane or building thermal envelope than I do inside. So I'm going to be deflating that balloon. I'm going to be pushing air out of that balloon through the hole that I've introduced. And so this is happening inside of our houses as well. And what we know is that a house defines a specific volume of air that doesn't change. That volume of air is constant. So if 1 cubic foot of air that is about the size of a basketball enters the house, then 1 cubic foot of air has to leave the house, and vice versa. If 1 cubic foot of air is pushed out of the house, then a cubic foot of air has to move into the house, because we always have a constant volume of air inside of our houses. So we also have these driving forces, or these things that create pressure differences across the building thermal envelope. And a lot of these things are very constant and out of our control. And the only way that we can get better control and predictability with regards to wind and what we call stack effect is if we build our houses tighter. They will have less impact. So wind and stack effect, again, are things that we don't have great control over beyond how tight we build the house. Wind is saying that whenever we have windy conditions and the wind is hitting the windward side of the house, we're going to have a positive pressure. On the leeward side of the house, we're going to have a negative pressure. And that pressure boundary conditions are set up inside the house as well, so that I can actually be pushing or sucking air out of the leeward side of the house when the wind is pushing in through holes on the windward side of the house. Now, stack effect is saying what is basically describing what happens to air as it warms. Air as it warms will rise, and as it rises, it hits that top plane of our home, and in essence, it's seeking a hole. It's trying to continue to move and rise, and it's creating this slight positive pressure on this high side of our home there to move ultimately out of our home to the outside there. And when any air leaves the house, it has to be removed, or it has to be replaced. So we have air coming in on the low side of our houses. And that's why you see a lot of contractors really spend a lot of time, especially in existing homes, air sealing the high side and the low side of our homes, and then working towards the middle. And then we have mechanical equipment that can create not only pressure differences across the building envelope, but pressure differences in specific rooms. So for example, if I have a master suite that has 5 supplies and 1 return, and they aren't equal in the amount of air that they're moving, I might be over pressurizing that master suite and pushing air against the building thermal envelope and ultimately out through holes in that envelope. Or I might be depressurizing that master suite. I can also create negative pressures just by turning on my kitchen hood, or turning on my dryer, or turning on a bath fan there. So these different pressures are things that we have a little bit more control over with mechanical equipment to try and create balanced pressures in our houses than we do with the wind and stack effect. But they're all what we call driving forces that create pressure differences across our holes that will create infiltration or exfiltration in our homes. And again, our goal is to create a tight house, and as tight as we possibly can, and to take that into account in our HVAC design here. So just to summarize, air is a fluid, just like water is a fluid. We need 2 things for that fluid to move. We need a hole and a driving force. If either is missing, we're not going to get that air moving across the hole. Remember that air in equals air out, and air out equals air in, and that we measure it in cubic feet per minute, and a cubic foot of air is about the size of a basketball. So you can imagine a basketball going into the house at the same time a basketball is going out of the house. Okay, so let's change our track here a little bit and talk about HVAC design and the impact of air movement and the thermal envelope on the HVAC design. So to begin with, our manual J, and we're really going to just be focusing on the manual J here. The manual J is taking into account the summer gains that we see in the summertime and the winter loss of energy through our building thermal envelope. And we now use a software to help us develop that manual J and develop that heating and cooling load for that house. Whereas in the past, we used a lot of rules of thumbs and estimates and guessing about how to actually size the equipment for that house. We should be limiting any guesstimate in this, and we should be using empirical data now when we're doing an HVAC load on that house. The manual load calculation really doesn't tell you the size of the HVAC system that needs to be installed. What it is doing is describing the load, and the load is different than the capacity of the equipment. The load tells us how much heat and cooling the house needs, and the capacity of the equipment needs to be sized so that it can meet that load, but that capacity of the equipment will generally be bigger than the load, because depending on the efficiency of the system, a certain amount of that capacity will be going up the flue or out of the house in other ways, and will not be meeting the true load requirements of that house there. So we want to not only define the load for the house, which is what the manual J is doing, but we want to pick the equipment in manual S that has the proper capacity to meet that load under worst case conditions there. So again, it's going to be slightly oversized, but we don't want it to be significantly or drastically or grossly oversized equipment here. So we have potentially oversized systems or undersized systems in our houses, often because our thermal envelope isn't being executed as it was supposed to be executed there. So for example, if I designed and developed the load in my manual J for a house that I assumed had an R19 bat in the exterior walls, and that bat was clearly compressed in its installation, and it was really achieving an R7 instead of an R19, well, my system was probably going to be undersized and not work properly there. And we might see that the HVAC contractor is going into the process assuming that the thermal envelope isn't going to be executed well, and therefore they're trying to compensate that by manipulating the manual J in some way to oversize the equipment there. So we need, again, to not only on the thermal envelope side, ensure that the specifications are there. In this case, this fiberglass bat is being installed. I can't, however, just walk in and say, yes, I see pink in the walls and walk out. I have to actually look at it, how it's been installed. And has it been installed to actually achieve the R value that has been specified? Or have the building cavities been used as a trash can instead? These are the things that we see on site. But on the HVAC side of the equation, that manipulation we can guard against as well. And there are eight things that we need to look at on the manual J to guard against any manipulation that the HVAC contractor might be doing because they don't have confidence in that thermal envelope. We need to look at the indoor design temperatures. We need to look at the exterior design temperatures. This creates the delta T, or temperature difference across our assembly, that is the biggest driver for the heat loss or heat gain in that house. We need to look at how they did their takeoffs for the square footage of the building thermal envelope and the different components there. We need to look at the R values and U values that they're using and the assumptions that they're using. Are they based off of the specifications of the house or not? The number of occupants that they're putting in and the appliances they're putting into that house, that infiltration and ventilation load, again, are they accounted for separately or not? The orientation of the house and the duct location, and ultimately leakage of that house there. So let's start by looking at the indoor design temperature. The indoor design temperature is governed by the IECC. The IECC says that the heating and cooling loads calculation shall be a maximum of 72 degrees for heating and a minimum of 75 degrees for cooling. We can look at the design information reports that come out of the softwares that are used to calculate the manual J, and we can pretty quickly see, are they using the right numbers or are they manipulating those numbers? And these numbers are coming from ASHRAE, who has developed this comfort zone chart, and have determined that those design conditions in cooling season and heating season are the ideal design conditions to create comfort in the interior of that house, regardless of what the temperature is outside the house. So that's why these are codified indoor design temperatures for heating and cooling seasons there. Now, the outdoor design temperatures are also created by ASHRAE, but they're created per climate zone or weather district, dependent on weather data that's been looked at over the course of about 30 years or so. So in the cooling season, it says that the dry bulb temperature is the temperature exceeded only 1% of the hours of the year. So in Denver, Colorado, for example, we have a design temperature of 91 degrees for our summer conditions. That means that only 1% of the hours over the course of the year that does the outside temperature get hotter than 91 degrees. Now, there could be some argument that global warming is changing that or something, but right now we're still required to use that 91 degrees here in Denver, Colorado. And depending on what climate zone you are, that could be different there, or will be different there. Now, on the heating side of the equation, it says the dry bulb temperature means that the temperature is above this point 99% of the time. So in Denver, we designed to 1 degree Fahrenheit in the winter conditions, which means that 99% of the time it's warmer than 1 degree. So it doesn't make sense to design to -5 or -10 degrees. In the same way, it doesn't make sense to design to 100 degrees or 110 degrees in the summer conditions, because those conditions are not seen often enough, and you're going to grossly oversize the system for the majority of the time that the system needs to run. And you have created a condition where you're going to get right-sized equipment that's going to run longer and create comfort in our houses there. So we need to check that these design conditions are actually used because they're creating that temperature difference across the building assembly in the worst case scenario to give us the ultimate load for that house in these worst case scenarios, and get systems that have long run times to create comfort in our houses. Now, the Building America program, which is a program through the Department of Energy, has done a significant amount of research on what happens when you manipulate these design conditions here. And you see that the design conditions have been manipulated, and you can see the change in the loads here. In this case, the heating load changed by 26%, and the total cooling load changed by 51%. You can also see if you're in a warm, humid climate that change is even more impactful, because you're starting to take into account latent loads, not just sensible cooling loads as well here. So we'll move on, and we'll see that change in the loads for these other components as well. So the next thing we can look at is the square footage of the house and the building envelope components. There's usually a design information sheet that gets turned into the jurisdiction, and you can see the area and volume that has been calculated for this house. A lot of jurisdictions and others will do their own calculation, or they might rely on the architect's calculation for the area of the house. And you just want to see that this number is within about 10% of your calculation. There, it's unlikely it's going to be exactly the same, but you're looking for gross differences that could be really impactful in these numbers here. If I have a 1,000 square foot house does 30, obviously a area of 3,495 doesn't make sense, and the volume doesn't correlate to that size house. And similar if I have a really large house. We can also look at the actual components. There are these worksheets that come out of Manual J calculations through the softwares. And if I look at the area of this wall system and the windows that have been added, do they make sense for the house that this design is working for? Or are they over calculating the wall area or under calculating the wall area? We want to look at both those things here. Next, we can look at the R values and U values of the envelope. In this case, I have a foundation wall that's supposed to be insulated with an R19, probably fiberglass blanket, and an exterior wall system that's 24 inches on center, blown fiberglass R23. So I go over and I look at the R value, and I have to look at how that R value has been translated into a U value. So we know that the R value is the reciprocal of U value. So if I take an R19, it should be 0.053, and I go over and I look at the U value that was actually entered, and I see it's 0.032. Well, that's a pretty significant difference there. That means that the lower the U value, the greater the R value. So it's actually saying that this foundation wall has been insulated significantly better than it has been in reality out there. So we want to make sure that those are working, those have been input properly, so that we're not getting any gaming of the system to oversize or potentially undersize, unbeknownst to the contractor, these systems here, these HVAC systems here. So again, I've got this calculation here. We can see some manipulation that happened with the building components of this house, and you can see the impact in the heating and cooling loads of this house. Again, pretty dramatic, but what we need to understand ultimately, and we'll see at the end here, is that they compound each other. Each of these mistakes, if multiple of these mistakes or manipulations happen, they get compounded over time in that ultimate design of the house. The number of occupants is another thing that we should be looking at. Each occupant inflates the load or increases the load. So the number of occupants are calculated by the number of bedrooms plus 1. It's the same way that we calculate the ventilation load for the house. So each occupant is about 230 BTU hours that should be added to the house. So if I have a 5-bedroom house, it would turn into 6 occupants and 1,380 BTU hours that would be added to the load of that particular house that needed to be looked at from a heating and cooling side equation. Now, we've seen some gross manipulations. In this case, 23 people were added to the house. That's a huge load. That's about 1/4 of a ton of additional air conditioning capacity that house actually didn't need there, which might mean that AC system is short cycling, or that the coil is freezing. All variety of different reasons why oversizing of the equipment shouldn't happen in our houses. You can look at these worksheets that come out of the Manual J, and you can see where the loads are being entered here. In this case, this 3-bedroom house has been entered with 4 occupants, and you can see that it was done correctly here. Appliance loads are also important to look at. Appliance loads are also defined in these worksheets, and you can see that they added 2,600 BTUs for appliances. Appliances are about 1,300 BTUs per appliance that's added to the system. So you'll usually see about 2 appliances like refrigerators added to the HVAC calculation. But if you see 5, 6, 7, you might ask a question of what's going on there and why that manipulation was happening. Infiltration and ventilation. So again, we want to be clear that these are 2 different inputs, and they should be thought of as separate inputs. Beginning with infiltration, how airtight the house is. Remember that the code is asking us to test houses now, to do a blower door test, and that house achieve a specific level of air tightness of the house. So you should never see an input that is leakier than 3 air changes per hour in climate zone 5 here in Colorado, or whatever climate zones you are. It shouldn't be leakier than what's required by code. So that's the first thing you should check. But in the Manual J infiltration calculation, you can use an estimate or you can use an accurate number here. The infiltration estimate process introduces a lot of uncertainty, subjectivity in the process of determining the air leakage of that home. It's based off of things like the size of the house and what they define as significant air sealing efforts in that house. The manual J will ask you to look at things like how many recessed cans are in the house without really knowing that they are airtight cans or non-airtight airtight cans in that house, how many fireplaces and what's the tightness of the windows in that house. But you don't necessarily know those things when it. So the estimated infiltration method in manual J is asking you to choose, is that house tight, semi-tight, average, loose, semi-loose, or loose in that. And this is the description of what that ultimately means. And you can look at the actual design information and determine what they chose here. In this case, they chose tight, which says that a structural panel has been used, that the corners, cracks, joints, and penetrations are sealed by meticulous workmanship. So how do I know if meticulous workmanship has been used and that has actually been used in the construction of that house when I've designed this HVAC system way before the house was ever being built here? So it's much better to actually use data, definitive data from blower door testing. So if you're working with a builder, a production builder, for example, that's built 100 houses and they tested 100 houses, you should have an air leakage rate average for that builder that would be much more accurate and better to use than these estimates through this guesstimate process that's allowed in manual J here. So infiltration shows up on these worksheets. You can see what method they've used, and you can see how many BTUs they've added for that particular method there. So in this case, it was tight, I believe, and they show it as 3,300 BTUs here. Now, newer versions of the software give you a little bit more data in the reports, so you can see a little bit more things. And this report is showing this ACH number. And the ACH number, you would think is air changes per hour, but also look that it's being reported in a decimal. And so a lot of people won't have a frame of reference for what that's actually telling us here. So there are a number of different ways to express air leakage of a home. The two that are used most often are air changes per hour and natural air changes per hour. It turns out that the IECC and the IRC are using air changes per hour, but manual J is actually using natural air changes per hour. Now, air changes per hour is pretty easily defined as the volume of air in a home that exchanges with air from the outside over the course of an hour. Natural air changes is really the same thing, except there's an adjustment that's made based off of the climate that that house is built in, how tall the house is, and the exposure that house has directly to wind. So how many trees are around it, how many other houses are around it, and so forth and so on. So you would do a calculation for air changes per hour, and you would do that same calculation for natural air changes, but you would make an adjustment to that air change per hour number using the N factor there that takes into account the height of the building and the exposure of the building and what climate that building is located in. And here's the N factor table and the calculation done for one house. And you can see the air change number is quite different than the natural air change number. First, it's a solid or whole number, not a decimal. And so you have to gain some type of frame of reference for what you're looking at. 0.18, is that an actually tight house? Or is it a house that is close to the requirement by the code? So in this case, 0.18 equals 2.67 air changes per hour. Well, that's really almost what the code, the minimum requirement for the code in Climate Zone 5 here in Colorado. Again, it depends a lot on the size of the house, but you need to make sure that you're looking at that number and have an understanding of how it equates to the actual house that you're approving there. So just to conclude that, natural air changes or the infiltration credit that you're giving to that house, we would strongly recommend that you use a blower door number versus the estimate process that Manual J allows, and that you enter it separately from mechanical ventilation, because mechanical ventilation is required by the code, and mechanical ventilation allows you to use a supply, exhaust, or balanced ventilation system that we see from the mechanical side of the code in the IRC. There is some confusion there. The confusion comes because supply and exhaust ventilation either pressurizes or depressurizes the house, and it uses the same holes that infiltration and exfiltration uses, but it puts it on a controlled system there. So when the system isn't running, you're still getting infiltration and exfiltration, but when the ventilation system is running, you're using the same holes that air is moving through. So there's some confusion amongst building officials or even HVAC contractors that whether to double dip in essence on the infiltration credit and not put into that calculation the ventilation load portion of that credit. And you'll see here that we have a central ventilation system installed in this house, and it adds a significant load to that house depending on how long you're running that system. If you're running an exhaust ventilation system 24 hours a day, it can be almost 8,000 BTU load on that house in the heating season. So again, the ultimate takeaway here is to ensure that you input the ventilation load separately from the infiltration load, and that infiltration doesn't equal ventilation. They're two different and distinct loads in our houses. And they can be looked at in these worksheets here. You can go back to the infiltration section here. You can look at room ventilation, and some of the reporting is better than others, but you need to dig it out of these reports and find what is the actual ventilation load for that particular house here. Again, you can see that the estimates here for this particular house are I guess I would say that most people understand air changes per hour at 50 pascals as measured from a blower door. So did you know that in this particular house that tight equals 1 air changes per hour? I mean, that's super tight. Semi-tight equals about what the code requires here in Colorado. And loose is really extremely leaky. So you need to look at what the contractor's assumption is and how does it relate to the actual specs and the actual building envelope that's been instructed. Going back to this study that was done by Building America, you can see that the impact is not as great, but again, it's compounded with other impacts or other mistakes that might be made on that drawing. So the last two that we have here before we close out are orientation. So orientation, the code doesn't require that we do site-specific and orientation-specific HVAC designs, especially for production builders. So if you do a design, a general design for that house or an estimate design for that house, some people call it a worst-case design for that house, you might have locations where the BTU loads vary a lot. In this case, the northeast orientation of the house versus the south orientation of the house varies by about 6,000 BTUs or half a ton of air conditioning there. So that house could be oversized or undersized depending on the orientation of the house. Now, Energy Star says that any orientation that is more than 6,000 BTUs different has to get its own HVAC design. But again, the code doesn't require that, but it is something that specific jurisdictions might consider looking at there. And it's something that you should look at in your HVAC review if you're a code official, for example. Duct location and duct leakage is another thing that can be looked at. The ducts inside the envelope or outside the envelope, how are they insulated? How tight are they? And what are their ultimate impacts on the ultimate sizing of these systems? you can see the heating load impact of 13% and the cooling load of 17%. And then what we ultimately see is how all of these things result in the total manipulation. So if you add up all of those different changes, those 8 things, we get a heating load that's 55% off and a total cooling load that's almost 100% off. And if you're in a warm, humid climate, that latent cooling load is almost 2% off. You know, we're getting to the point where we are hugely, grossly oversizing or undersizing our equipment, depending on how it goes. But it's not right. It's not right size. We're not going to get a system that's efficient. We're not going to get a system that works and performs for that house here. The last thing I wanted to point out is there are 2 other air streams that aren't accounted for very well. One is combustion air, which is accounted for in our IECC code, and I'll show you that in a second. But the other is makeup air that's coming into the house for kitchen hoods, for example. The code says that you have to provide makeup air. So if you're providing makeup air, you might add an additional appliance to your load in that house for that makeup air, so that you're at least taking that into account in some way there. Now, for combustion air, the code does say that rooms containing fuel burning appliances that are bringing in combustion air, they're atmospherically vented equipment, that you really are required to build a sealed room that defines the building envelope so that that room is outside the building envelope. It has airtight doors that are fully gasketed. All the penetrations through that building envelope are airtight and sealed there. The door is shut during the blower door test through that. All ducts inside that room are insulated properly. All these things should happen. I would say in general, most jurisdictions are not enforcing this or doing a good job with this. But in essence, if you're not using sealed combustion appliances, you're supposed to have an airtight room that separates the combustion air from the rest of the air inside of that house. Okay, so to conclude, I hope that I've been able to demonstrate the synergistic effect between the building thermal envelope and the HVAC design. If you are not designing your systems with the true specifications of the house, you're going to have a problem. And if you're not carrying out the true specifications of the house in that building envelope and getting a tight house and ventilating it correctly, there are going to be comfort issues, callback issues, potential building durability issues in that house. We've clearly defined 2 of the 4 main air streams in the house that that are incorporated in the HVAC design load, manual J load. That's air leakage and ventilation. Those are truly 2 separate things. The air leakage is talked about in terms of infiltration and exfiltration. Ventilation is the air that you're bringing in for the houses, because when we build our houses tight, we need to ensure that there's fresh air and background moisture control. But we also have combustion air and makeup air that we need to take into account for. Any air that's coming into the house is leaving the house, so that notion of air in equals air out. And all that air is part of the load, the manual J load of that house. So we want to build our houses tight, ventilate them right, gain control and predictability of the airflow in their houses, because air is a transport mechanism. It's transporting heat, it's transporting pollutants, it's transporting moisture around our houses. And we need that control and predictability to have an efficient, a durable, a comfortable, and a safe house for our occupants. So thanks so much for joining us today. Remember that there are other trainings that are coming up, and there's great ways to get technical assistance through this Colorado Energy Office project that's going on. And if you have any questions for me, don't hesitate to reach out to me, either through my email or on Instagram or through my website. I'm available to answer questions now or in the future.
Thanks, Robbie. Yeah, Robbie and I will stay on the line for a little bit longer. I know we're at the hour now. So thank you all for joining us. Looks like we do have a question here, Robbie. I have observed that system designers incorporating the default ventilation requirements from the Manual J software end up specifying excessive whole house mechanical ventilation compared to the minimum requirements of the 2018 IRC section M1505. This would represent an unnecessary energy penalty to the homeowner. Do you have any thoughts about why this is happening in the designer workflow?
Well, my guess is that they're either using, the code allows you to design your ventilation system either by using a table that's defined in ASHRAE 62.2, the ventilation standard, or by using the calculation in that standard in the newer codes. The older codes like the 2012 only use the table, and the table generally is just using the size of the house and the number of bedrooms, and doing that in ranges that can create instances where you have great overventilation of a house, and that overventilation of the house would increase the loads that are looked at as well. So they might be using the table versus the formula there, and creating an uncomfortable house because of that. That's the only thing I can think of off the top of my head.
Thanks, Robbie. Okay, I'm gonna go ahead and stop